In this video, we're going to show you the question 6s from previous final exams. Since about 2013, question 6 has always been a bit more challenging than the other questions. There's never any guarantee that finals will look similar to previous finals. This is extra true for 2020 since we're not sitting down in the same room to write the final on a piece of paper. Now, what do we mean by challenging? Usually this means you need to combine different concepts or take an old concept and put it in a new context. The purpose of these questions is usually to separate out who should earn an A from who should earn an A+. So what does that mean for your strategy when you see a particularly challenging question? First, you should go through the rest of the exam and feel like you've really put in your time on those problems. Only after you've done that should you spend a lot of time on a problem that may or may not work out in the time allotted for the test. Equally as important as managing your time is managing your emotional state. When you come to a really difficult problem, it can be very upsetting. But remember how tests are usually written. They're written with a range of difficulties in mind. A common practice when writing an exam is to break down the points you expect people to get at different understanding levels. So we think about what a passing student should know. If a passing student should earn, say, 50% on an exam, then a common way of writing an exam is to make sure that 50% of the points are written at that level. On the other end of the spectrum, if separating an A from an A+ should be the difference of 10 percentage points, then 10 percentage points should be at that A+ level. So if you're really gunning for top of the class, this is going to give you a different strategy from someone who is perfectly fine walking away with a B. But again, the important thing is to not let yourself get derailed. When you blast through those first couple problems because they feel very easy to you, that is not something to throw away. That is built into the test, rewarding you for demonstrating that knowledge. So let's look at some of these problems. Take a second, read this question, and think about how you might solve it. I would say this question falls under the category of using an old concept in an unfamiliar setting. I want to know if it's possible that I multiply two functions together, the area under that combined curve is 0, but the area under the original curves are not 0. So let's think about how it can be that the area under a function is 0. It could be that the function itself is just 0. It could also be that the function has an equal amount of area above and below the x-axis, because the integral is net area. So can we get this behavior by multiplying two functions that do not exhibit this behavior themselves? In the first case, I can't have one of my functions be 0 all the time, but I could have each function be 0 some of the time. So maybe f of x looks like this, and g of x looks like this. F of x could be 0 if x is less than a half, and 1 if x is greater than a half. G of x can be the opposite. And then f times g of x is just 0. So this is one example of why the answer to this question is yes, this can happen. If we want to think of another example, we can think of this behavior on the bottom. Let's try to make things a little bit easier on ourselves by making a little bit of an easier target function. Let's just make this +1 and -1. And what I can do is I can use g to change the sign of f. So if g is +1, f stays the same. If it's -1, it becomes negative. So I can't make g just +1 half the time and -1 half the time, because then I would have the area under the curve of g be equal to 0, and that's what I'm trying to avoid. But I could have it be +1 not half of the time and -1 not half of the time. So let's think about making a g that's maybe something like this. Now I need to figure out when f should be 1 and when f should be -1. I want the product to be +1 from 0 to a half. So g should be +1 from 0 to a quarter, and then -1 from a quarter to a half. Then from a half on out, I want my whole function to be -1. G is -1, so f of x should be +1. Now when I multiply these functions together, I get +1 when x is less than 1/4. When x is bigger than 1/4 and less than 1/2, I also get +1. And when x is bigger than 1/2, I get -1. So the product is what I wanted it to be. And the area under these curves individually is not 0. The area under f of x is positive, and the area under g of x is negative. So often with a challenging problem, you might not jump to the easiest answer right away. That's, of course, perfectly fine. This problem asks us to evaluate a limit. We can't immediately plug in x as 0, because then I would be dividing by 0. We also have this x in the upper bound of a definite integral, and that makes us think of the fundamental theorem of calculus, part 1. I would like to differentiate this because it reminds me of the fundamental theorem of calculus, part 1, and the definition of derivative uses a limit. So I'm going to combine my intuition that I want to use the fundamental theorem of calculus with my intuition that maybe I can turn this limit into a limit that matches the definition of a derivative. Now, something that comes up a lot on these question 6s is there will be something that looks quite complicated but doesn't need to be treated as complicated. This thing is just, for our purposes right now, some function of f. So I'm going to write it as just f of x. So I'm going to define f of x to be this function of x. Now I'm going to rewrite my limit and hope that that makes things a little bit clearer to see. This is big F of x times 1 over x. So this is already looking a little bit nicer. Now let's remember different ways to write the definition of a derivative. One of the ways we can write it is like this. Another way we can write it is like this. The second one seems to match better because I have an x, not an h, so this variable and that variable match. Since I don't have it subtracted by something, I can set a equal to 0. Now in the numerator, I don't have f of 0, but let's think about what f of 0 would be. So let's come back down here to our definition. F of 0, oops, there's an x there. F of 0 should be the integral from 0 to 0 of something dt. This is the area under the curve from 0 to 0, which is 0. Because the top and bottom bounds are the same, there's no area in there. So actually for this f of 0 is 0. So I can simplify this even further to f of x minus 0 over x, and now we see that's exactly what we're meant to evaluate. So I can evaluate this as f prime of 0. Now I get to apply the fundamental theorem of calculus, part 1. I want to differentiate this function with respect to x. This is a compound function. It's a function of a function. This is my inside function. If, instead of 2017 times x, I just had x, then my derivative would be the square root of 2017 plus x to the power 2017. If this were just an x, I would plug it in for t and be done. It's not x, it's 2017 times x, so the chain rule says I need to multiply by the derivative, which is 2017. So this is the derivative of f in general. My question is asking me for this derivative evaluated at 0. So this is the square root of 2017 plus 0 times 2017. Or if you like, that's 2017 to the power 3/2. There's a few ways to evaluate this integral using techniques we've learned in class. Some of them are easier to come up with than others. So I'll show you two ways of doing it. The first one will be a little bit easier to come up with, but a little bit harder to actually do. I might notice that I can factor out an x. Now, it looks like maybe a substitution rule problem. There's not a real obvious substitution, but something we've seen in the past is sometimes it works to set u to be the denominator. Why don't I try setting u to be this difficult part of the denominator? Then my derivative is 2015 times x to the 2014. Now this doesn't exactly show up multiplied, but I could force it to show up multiplied by just multiplying the top and bottom by it. Now the bottom is going to simplify to be something that can easily be replaced with u. (2015x to the 2014 dx), that's exactly du. X to the 2015, that's u plus 1. Now we've made it simpler, but it's still not trivial. So how can I evaluate this? I can evaluate it by using the method of partial fractions. My integrand can be written as some constant over u plus some constant over u plus 1. Now I'll skip the algebra and tell you this is 1 and negative 1. So that's one way to do the antiderivative. It turns out there's an even easier way. I'm going to divide the top and bottom by the highest power of x, 2016. Now I'm going to use the same intuition as last time, which is that the denominator is often a nice thing to have show up in your u substitution. And there we have it. Something to note is that this actually is equivalent to our previous answer. You'll have to do a little bit of work with log rules in order to show that they're the same. In 2015, we're given information about one series and asked about a related series. What we're told about this series is just that it converges and that our a sub n's have positive terms. Then we take those same a sub n's and we multiply them by 2 to the power n, and we want to know whether that new series converges or diverges. So let's think about what's going on with our a sub n's. By the divergence test, if the limit as n goes to infinity of 1 minus n is anything other than 0, then the series I get by adding up those terms diverges. We know that series converges, so it must be the case that this limit is indeed equal to 0. In particular, that means the limit as n goes to infinity of my a sub n terms is 1. So now let's think about what that means for the series we're asked about, 2 to the power n times a sub n. The limit as n goes to infinity of those terms is going to be infinity, because when n gets really large, these just look like 1, whereas 2 to the power n is growing without bound. So by the divergence test, the series we're asked about diverges. That finishes question A. Question B is about the radius of convergence for power series, and in 2020 this has been cut from our syllabus, so I'm not going to bother going over it. Actually, for the older exams, the questions asked are also related to topics that have been cut from the syllabus for 2020. 2014 asks about telescoping series, and 2013 asks again about convergence of power series. So we are going to end the video here.